Right now, two beams of light are crossing paths inside your eyes. Trillions of photons from your screen are passing through scattered light from the room around you, and not a single one of them notices the other. They slide through each other like ghosts. No collision, no deflection, nothing. Light, it seems, is completely invisible to itself. But here is what almost nobody knows. Under the right conditions, two photons can actually collide. And when they do, something happens that sounds like it belongs in science fiction. The photons can vanish, and in their place, matter appears. Actual physical particles pulled into existence from nothing but pure light. Tonight, we're going to explore exactly how, why, and when light can do the impossible, and why it almost never does. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you do every single day without even thinking about it. Right now, wherever you are, light is passing through light. Photons from your screen are crossing paths with photons bouncing off the walls, the ceiling, the furniture around you. If you're sitting near a window, sunlight is streaming through the glass and mixing with the artificial light inside the room. These beams are occupying the same space at the same time, and none of them are affecting each other, not even slightly. They pass through one another perfectly, completely, as though the other beams simply do not exist. This is something so ordinary that you have probably never stopped to think about how strange it actually is. Think about what happens when two solid objects meet. You throw two baseballs at each other and they collide. They bounce off one another, change direction, maybe even crack apart. That is what we expect from physical objects. They interact, they push, they deflect, but light does not behave this way. Two beams of light can cross in the exact same point in space, overlap completely, and then continue on their way as though absolutely nothing happened. No deflection, no distortion, no collision of any kind. Each beam emerges from the crossing point exactly as it went in, unchanged in every measurable way. You have seen this countless times without realizing what you were witnessing. Think about a concert or a laser show. Dozens of laser beams sweep through the air, crossing one another constantly. Red beams slice through green beams. Blue beams intersect with white beams. Every single beam passes through every other beam without the slightest visible effect. No beam gets bent or scattered or dimmed by another beam crossing its path. Or think about driving at night. Headlights from cars going in opposite directions cross constantly. The photons from your car's headlights pass directly through the photons from the oncoming car's headlights, and neither beam is disturbed. If light interacted with itself the way solid objects do, driving at night would be impossible. Headlights would scatter off one another, creating a blinding, chaotic mess of ricocheting light in every direction. Or consider something even more fundamental. Look up at the night sky on a clear evening. Every star you see is sending photons toward your eyes. But those photons are not traveling through empty space alone. They are sharing that space with photons from every other star, from distant galaxies, from the faint cosmic microwave background that fills all of space, from every object in the universe that emits or reflects light. Trillions upon trillions of photons are crisscrossing the cosmos in every direction at every moment, and they all pass through one another without the slightest disturbance. If photons scattered off each other the way billiard balls do, the night sky would be a uniform, featureless blur. You would not be able to see individual stars because their light would be constantly scattered and redirected by all the other photons filling space. The fact that you can look up and see a clear, sharp point of light from a star hundreds of light years away tells you something profound about how light behaves. It tells you that photons are, for all practical purposes, completely invisible to one another. Light is transparent to itself. That is the simple version of what is happening. But to understand why this is the case, and more importantly, why this transparency is not quite absolute, we need to understand what light actually is. And that question, as simple as it sounds, took humanity centuries to answer. Because light is one of the most deceptive phenomena in nature. It is everywhere. It is the first thing you experience when you open your eyes each morning. It defines how you perceive the entire world around you. And yet, for most of human history, nobody had any idea what it actually was. People could see with it, navigate by it, use it in countless practical ways. But the fundamental nature of light remained one of the deepest and most stubborn mysteries in all of science. The ancient Greeks debated whether light was something that flowed out of your eyes and touched objects, or something that flowed from objects into your eyes. They never resolved the question. Centuries later, Isaac Newton believed light was made of tiny particles, which he called corpuscles. He imagined light as a stream of small, fast-moving objects flying from a candle flame or the sun to your eye. This seemed to explain why light traveled in straight lines and cast sharp shadows. It behaved the way you would expect a stream of particles to behave. But around the same time, other scientists, most notably Christian Huygens, argued that light was a wave. Waves could explain phenomena that particles could not, like how light bends slightly around corners, a phenomenon called diffraction, and how two light beams could create patterns of bright and dark bands when they overlapped, a phenomenon called interference. For well over a century, the debate went back and forth. Particles or waves? Newton's immense prestige gave the particle theory a considerable advantage for a long time, but the wave theory kept quietly gaining evidence. In 1801, a British scientist named Thomas Young performed an experiment that seemed to settle the question once and for all. He shone light through two narrow slits cut into an opaque barrier, and observed the pattern it created on a screen behind them. If light were made of particles, you would expect to see two bright bands on the screen, one behind each slit, where the particles hit. Instead, Young saw a series of alternating bright and dark bands stretching across the screen, an interference pattern. This was exactly what waves would produce. When the peaks of two waves arrive at the same point, they add together and create a bright spot. When a peak arrives at the same point as a trough, they cancel each other out and create a dark spot. Only waves could produce this pattern. Young's experiment was powerful, almost irrefutable evidence that light is a wave, and for a time, that seemed to be the definitive answer. But what kind of wave was it? Water waves need water. Sound waves need air or some other material to travel through. What was light waving through? Scientists proposed a mysterious substance they called the luminiferous ether, an invisible medium that supposedly filled all of space and carried light waves the way air carries sound. But the ether was never detected. No experiment could find the slightest trace of it. In 1887, Albert Michelson and Edward Morley performed a famous experiment designed to detect the ether by measuring whether light traveled at different speeds in different directions as Earth moved through this supposed medium. They found no difference whatsoever. The speed of light was the same in every direction, regardless of how Earth was moving. The ether did not seem to exist. Meanwhile, in the 1860s, a Scottish physicist named James Clerk Maxwell made one of the greatest intellectual breakthroughs in the entire history of science. He unified electricity and magnetism into a single, coherent mathematical theory. And in the process, he discovered something extraordinary about the nature of light. Light, Maxwell showed, is an electromagnetic wave. It is a ripple in the electric and magnetic fields that propagates through space at a speed of about 300,000 kilometers per second, the speed we now call the speed of light. Maxwell's equations describe how electric and magnetic fields behave and interact with each other. They reveal that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This interplay means that once you set up a disturbance in these fields, it sustains itself indefinitely. The electric field generates the magnetic field, and the magnetic field regenerates the electric field, and this self-sustaining oscillation propagates outward through space as a wave, requiring no medium whatsoever. That wave is light. What you perceive as visible light, the colors of the rainbow from red to violet, is just a narrow band of electromagnetic waves with wavelengths between about 380 and 700 nanometers. But electromagnetic waves come in a vast range of wavelengths, far beyond what your eyes can detect. Radio waves can be meters or even kilometers long. Microwaves are a few centimeters. Infrared radiation sits just below the visible spectrum. Ultraviolet sits just above it. X-rays have tiny wavelengths, and gamma rays have the smallest wavelengths of all, carrying enormous energy per photon. All of these are the same fundamental thing. They are all electromagnetic waves. They differ only in their wavelength and the energy they carry. And here is where we arrive at the crucial point about why light passes through light. Maxwell's equations have a special mathematical property. They are linear. This is a technical term, but the concept behind it is simple and incredibly important. In a linear system, if you have two separate solutions, you can add them together and the result is also a valid solution. Applied to light, this means that if one beam of light is a valid solution to Maxwell's equations, and another beam of light is also a valid solution, then both of them existing in the same space at the same time is also perfectly valid. The two waves simply add together, point by point, field value by field value, and the combined result is just the sum of the two individual waves. Where they overlap, the fields combine temporarily, and you might see a brief increase or decrease in brightness depending on whether the waves happen to be in step or out of step. But when they pass through each other and separate, each wave continues exactly as it was before, unchanged, undisturbed, as if the other wave had never been there at all. This is called the principle of superposition, and it is one of the most important ideas in all of wave physics. You can see superposition at work in other types of waves too. Drop two pebbles into a perfectly still pond. Two sets of circular ripples spread outward across the surface. Where the ripples overlap, they combine. Where two crests meet, you get a temporarily higher crest. Where two troughs meet, you get a temporarily deeper trough. Where a crest meets a trough, they cancel each other out and the water barely moves. But after the ripples pass through each other, each set of ripples continues spreading outward as though it never encountered the other one. The waves do not bounce off each other. They do not deflect each other. They simply add together in the overlap region, and then continue on their way, unchanged. Light does exactly the same thing. Two beams cross, their electric and magnetic fields add together in the overlap region for a fleeting instant, and then each beam continues on its original path, completely unaffected. This is why crossing flashlight beams do not interact. This is why laser beams at a concert pass through each other cleanly. This is why the night sky is not a featureless, blurry glow. Now, you might be wondering something deeper. Why are Maxwell's equations linear in the first place? Why does superposition hold for electromagnetic waves? The answer has to do with the nature of light itself, and more specifically, with a property that turns out to be absolutely critical for everything we are going to explore tonight. Photons carry no electric charge. The electromagnetic force is the force between electrically charged particles. Electrons carry negative charge. Protons carry positive charge. These particles create electromagnetic fields around themselves, and they respond to the electromagnetic fields created by other charged particles. That is how the electromagnetic force works at its core. Charged things create fields, and charged things feel fields. An electron creates an electric field that extends outward in every direction. Another electron nearby feels that field and is pushed away. That push, that repulsion between two negatively charged particles, is the electromagnetic force in action. But photons, the individual packets of electromagnetic energy, do not carry electric charge. A photon is electrically neutral. Its charge is exactly zero. This means that in the classical picture, one photon does not create a force on another photon. There is no electromagnetic push or pull between them. Compare this to electrons. Two electrons repel each other because they both carry negative electric charge. Each one creates an electric field, and the other one feels that field, and this is pushed away. This is a direct interaction between two charged particles, mediated by the electromagnetic force. Photons simply cannot do this. Since they carry no charge, they do not create the kind of field disturbance that would push or deflect another photon. And since they carry no charge, they do not respond to the fields of other photons either. They are, in a very real sense, blind to each other. Two photons passing through the same point in space exert essentially zero electromagnetic force on one another. Think of it this way. Imagine a mail carrier whose job is to deliver letters between people in a neighborhood. The mail carrier picks up a letter from one house, carries it across town, and delivers it to another house. Now imagine two mail carriers crossing paths on the sidewalk. They do not deliver letters to each other. They are not part of the communication network in that way. They are the means by which messages travel, but they do not send or receive messages themselves. Photons are somewhat like those mail carriers. They are the carriers of the electromagnetic force. They mediate the interaction between charged particles. An electron emits a photon, and another electron absorbs it, and that exchange is how the electromagnetic force is transmitted. But the photons themselves carry no charge, so they do not participate in the electromagnetic interaction the way charged particles do. They carry the force, but they do not feel it themselves. This is a deep and fundamental point about how nature is structured. In classical electromagnetism, photons do not interact because they have no charge. And because they have no charge, the equations governing their behavior are linear. And because the equations are linear, superposition holds. And because superposition holds, light passes through light. It is all connected in a tight, elegant chain of reasoning. The non-interaction of light beams is not some accidental quirk of nature. It is a direct and unavoidable consequence of the fundamental structure of the electromagnetic force. The force is carried by particles that do not themselves participate in the force. This is not true of all forces in nature, by the way, and this comparison will matter later. The strong nuclear force, which holds the nuclei of atoms together, is carried by particles called gluons. And gluons, unlike photons, do carry the charge of the strong force, which physicists call color charge. Gluons interact with each other. They feel the very force they carry. This makes the strong force profoundly more complicated than electromagnetism and gives it very different properties. But for electromagnetism, the carrier particles are neutral. Photons do not interact with each other at the classical level. End of story. Or so it seemed for a very long time. Because here is what makes this entire topic so fascinating. Everything I have described so far, the superposition principle, the linearity of Maxwell's equations, the non-interaction of photons, all of it is correct at the classical level. In classical electromagnetism, two beams of light genuinely do not interact at all. The theory predicts zero interaction, and experiments at everyday energies confirm this prediction with extraordinary precision. But classical electromagnetism, brilliant and spectacularly successful as it is, turned out not to be the complete picture. It is an approximation, an incredibly good approximation that works beautifully in the world of everyday experience. But at the deepest level of reality, at the quantum level, the rules are subtly different. And those subtle differences open the door to something truly remarkable. To understand how, we need to take a brief detour through one of the greatest revolutions in the history of physics. In the early 20th century, scientists discovered that light is not just a wave, it also behaves like a particle. This was deeply confusing and profoundly unsettling at the time. Thomas Young's double-slit experiment had shown conclusively that light is a wave. Interference patterns, diffraction, and every other hallmark of wave behavior had been demonstrated repeatedly throughout the 1800s. The evidence seemed overwhelming and settled. But then came problems that waves alone couldn't explain. In 1900, the German physicist Max Planck was trying to explain the spectrum of light emitted by hot objects, what physicists call blackbody radiation. Classical wave theory predicted that a hot object should emit infinite energy at very short wavelengths. This was obviously absurdly wrong. Hot objects do not emit infinite energy. They would destroy the universe if they did. Planck found that he could fix the problem, but only by making a radical assumption. He proposed that energy is not emitted continuously like a smooth wave. Instead, it is emitted in discrete, indivisible packets, which he called quanta. Each quantum carried an amount of energy directly proportional to the frequency of the light. Higher frequency light came in larger packets. Lower frequency light came in smaller packets. This was strange, almost bizarre. It suggested that the smooth, continuous electromagnetic wave was actually made of individual chunks of energy. Planck himself was uncomfortable with the idea, and initially treated it as a mathematical trick rather than a description of reality. 5 years later, in 1905, Albert Einstein took Planck's idea and pushed it to its logical conclusion. Einstein was studying the photoelectric effect, the phenomenon where light shining on a metal surface causes electrons to be ejected from the surface. The puzzle was that dim light of a high frequency could eject electrons, but bright light of a low frequency could not, no matter how bright you made it. If light were purely a classical wave, the intensity should be what matters most. More intense light delivers more energy per second. But that is not what experiments showed. Einstein proposed that light actually consists of individual particles, which we now call photons. Each photon carries a specific amount of energy determined by its frequency. Higher frequency means higher energy per photon. When a single photon with enough energy strikes an electron in the metal, that electron gets kicked out. If the individual photon does not carry enough energy, then no number of low-energy photons hitting the surface will eject an electron. The interaction is all or nothing, one photon at a time. This was revolutionary. Light is both a wave and a particle, not one or the other, but somehow, bewilderingly, both. This is called wave-particle duality, and it remains one of the strangest and most fundamental principles in all of quantum physics. A photon is not a tiny marble bouncing around in space. It is not a smooth, continuous wave rippling through an invisible field. It is something else entirely. Something that doesn't have a clean analogy in everyday human experience. It behaves like a wave when you design an experiment to test wave properties, producing interference patterns and diffraction effects. It behaves like a particle when you design an experiment to test particle properties, arriving at a detector one at a time with a definite amount of energy. It is as if nature is quietly telling us that our intuitive categories of wave and particle are only approximations. Useful mental models that capture certain aspects of reality but miss the deeper, stranger truth underneath. The photon is what it is. Our everyday language simply does not have the right word for it. But here's the important thing for our central question. Whether you think of light as a wave or as a particle, the conclusion at the classical level remains the same. Photons do not interact with each other. In the wave picture, superposition holds. In the particle picture, photons carry no charge. Either way, light should pass through light, without any interaction whatsoever. And in everyday life, this is exactly what happens. You have never seen two flashlight beams bounce off each other. You have never seen a laser beam deflect another laser beam. You have never noticed the light from one star being scattered or dimmed by the light from another star crossing its path. In everyday experience, with everyday light at everyday energies, photons simply do not interact. The probability of two visible light photons affecting each other when they cross paths is so phenomenally, absurdly, vanishingly small that you could watch every photon in the observable universe cross paths with every other photon for the entire 14 billion year history of the cosmos, and still almost certainly never see it happen. Not once. The odds are so staggeringly tiny that for all practical purposes, the classical prediction that photons do not interact is as close to perfectly correct as any prediction in science. So when you look at two flashlight beams crossing in a dark room and you observe that they pass cleanly through each other without any effect, your eyes are not deceiving you. That is genuinely what is happening, at least to an extraordinarily precise approximation. The classical picture works brilliantly. Maxwell's equations, the superposition principle, the electrical neutrality of photons, all of it holds up flawlessly under normal conditions. But that word, approximately, is doing critical work. Because approximate non-interaction is not the same as absolute non-interaction. And this distinction, subtle and seemingly academic as it may appear, cracked open one of the most fascinating and surprising chapters in the entire history of modern physics. In the 20th century, physicists built a deeper theory, one that went beneath classical electromagnetism to reveal the quantum machinery humming away underneath. That theory is called quantum electrodynamics, and it showed that the vacuum of empty space is not what it appears to be. It is not truly empty. It is not inert. It is not a featureless void. Instead, it is underlaid by quantum fields, restless, dynamic, ever-present fields that fill every point in space and time. And these fields, invisible and silent as they are under normal conditions, are what allow two photons, under extreme enough circumstances, to feel each other's presence and interact in ways that classical physics could never have predicted. There is one more thing worth appreciating before we go deeper, because it puts the stakes of this story into perspective. The fact that light does not interact with itself and everyday energies is not just a curiosity for physicists to puzzle over. It is absolutely essential for the universe to function the way it does. Every star in the sky is broadcasting photons in every direction at every moment. The space between stars is flooded with photons, billions of them passing through every square centimeter every second. If these photons scattered off each other even slightly, information carried by light would be scrambled beyond recognition. You could not see distant objects clearly. Telescopes would be useless. The night sky would be a washed-out, featureless glow. Vision itself would not work because the photons entering your eye would be constantly deflected by other photons before they could form a coherent image on your retina. Optical communication, photography, astronomy, even the basic act of seeing, all of it depends on the fact that photons pass through each other without any interaction under normal conditions. The transparency of light to itself is not a minor detail. It is one of the foundational properties of the universe that makes everything we know possible. And yet, hidden beneath this cosmic transparency is a quantum mechanism that allows the seemingly impossible. Two photons, when they carry enough energy and meet at the right angle, can interact. They can scatter off each other. And if their combined energy is high enough, they can do something even more astonishing. They can vanish entirely and leave behind something new. Matter. Real, physical, measurable particles conjured from nothing but the energy of pure light. Understanding how this works requires us to leave the comfortable, familiar world of classical physics behind and step into the strange, beautiful, counterintuitive realm of quantum electrodynamics. And that is exactly where we are going next. We left off at the edge of a cliff. Classical physics had given us a clean, beautiful answer to the question of whether photons interact. They do not. Maxwell's equations are linear. The superposition principle holds. Photons carry no electric charge. Light passes through light with zero interaction. Case closed. Except it was not closed. Because in the early decades of the 20th century, physicists began dismantling the classical picture of reality piece by piece, replacing it with something far stranger, far more subtle, and far more powerful. And the theory they built, the deepest and most precise theory of light and matter ever conceived, quietly revealed that the classical answer was not quite right. Two photons can interact. Not easily, not often, but they can. And the mechanism that allows it is one of the most beautiful and bizarre ideas in all of physics. To understand it, we need to talk about what empty space really is. Because the answer to that question, more than anything else, is what separates classical physics from quantum physics. And it is what opens the door to photon-photon scattering. In classical physics, empty space is exactly what it sounds like. It is nothing. A void. Remove every atom, every particle, every grain of dust from a region of space, and what remains is perfectly, absolutely empty. There is nothing there. Nothing can happen in that vacuum because there is nothing present to make anything happen. The vacuum is inert, featureless, and boring. Quantum physics tells a completely different story. In quantum physics, empty space is not empty at all. It is filled with fields, not the electric and magnetic fields we talked about earlier, though those are part of it. Quantum physics says that every type of particle in nature has a corresponding quantum field that extends across all of space. There is an electron field. There is a quark field. There is a photon field, which is really the quantum version of the electromagnetic field. There are fields for neutrinos, for muons, for every fundamental particle physicists have ever discovered. These fields are everywhere. They fill every cubic centimeter of the universe, from the space inside your body to the void between the most distant galaxies. Now, what does it mean for a field to fill space? A field is simply a quantity that has a value at every point. Think of temperature as an analogy. At every point in a room, the air has a temperature. That temperature might vary from place to place, warmer near the heater, cooler near the window, but every point has a value. Temperature forms a field across the room. Quantum fields are similar, except instead of describing temperature, they describe the potential for particles to exist. And here is where it gets strange. These fields are never perfectly still. Even in the lowest possible energy state, even when no particles are present at all, quantum fields are restless. They fluctuate. They jitter. They vibrate with a kind of irreducible, built-in noise that can never be eliminated, no matter how perfectly you cool the system or isolate it from disturbances. This is a direct consequence of the Heisenberg uncertainty principle, one of the foundational pillars of quantum mechanics. The uncertainty principle says that certain pairs of physical properties cannot both be precisely determined at the same time. The more precisely you know one, the less precisely you can know the other. For quantum fields, this means you cannot simultaneously know the field's value and its rate of change with perfect precision. There is always some uncertainty, some fuzziness, some unavoidable jittering. Even in a perfect vacuum, the fields are never exactly at zero. They hover around zero, fluctuating up and down in tiny, random amounts. These fluctuations are called quantum vacuum fluctuations, and they are not just theoretical. They have measurable, observable consequences. One of the most famous is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and confirmed experimentally decades later. If you place two perfectly flat, uncharged metal plates very close together in a vacuum, closer than a millionth of a meter, they experience a tiny but measurable attractive force pushing them together. This force arises because the quantum field fluctuations between the plates are slightly different from the fluctuations outside the plates. The plates restrict which fluctuations can exist in the narrow gap between them, creating an imbalance that produces a real physical force. The Casimir effect has been measured in laboratories. It is real, And it tells us something profound about the nature of empty space. The vacuum is not empty. It is a seething, dynamic medium filled with the restless activity of quantum fields. Now, here is why this matters for photons. Remember, in the classical picture, photons do not interact because they carry no electric charge. They are blind to each other. But in the quantum picture, the vacuum between and around those photons is filled with quantum fields, including the electron field. And the electron field does carry electric charge. Electrons have charge. Positrons, the antimatter partners of electrons, have charge. The electron field, even in its quiet, fluctuating ground state, is a field of charged particles. And this changes everything. When two photons pass through the same region of space, they do not interact directly with each other. That part of the classical picture remains true even in quantum electrodynamics. One photon does not reach out and push the other photon, but each photon can interact with the electron field. A photon is, after all, a quantum of the electromagnetic field, and the electromagnetic field is precisely the field that couples to electric charge. So a photon can briefly disturb the electron field as it passes through, and the electron field, in turn, can influence another photon passing through the same region. The electron field acts as an intermediary, a kind of quantum middleman that allows two photons to feel each other's presence, indirectly. Think of it this way. Imagine two boats on a perfectly calm lake. The boats themselves do not touch each other. They are far apart. But as each boat moves, it creates ripples in the water. And those ripples spread outward and eventually reach the other boat, causing it to bob slightly. The boats interact not by direct contact, but through the medium of the water. The water is the intermediary. In a very loose sense, the electron field plays a similar role for photons. Two photons do not interact directly, but they can both disturb the electron field, and those disturbances can communicate between them. But I want to be careful with this analogy because it can easily be pushed too far. What actually happens in the mathematics of quantum electrodynamics is more subtle than ripples on a lake. The theory describes this process using a mathematical framework developed in the middle of the 20th century by some of the most brilliant physicists who ever lived, including Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. These three independently developed the mathematical tools of quantum electrodynamics and shared the Nobel Prize in Physics in 1965 for this work. Feynman's contribution included something that has become one of the most iconic images in all of physics: Feynman diagrams. These are simple, elegant drawings that represent mathematical terms in the calculations of quantum electrodynamics. In a Feynman diagram, straight lines represent particles like electrons and positrons. Wiggly lines represent photons. And the points where lines meet, called vertices, represent interactions between particles and photons. Each diagram corresponds to a specific mathematical expression, and by drawing all the possible diagrams for a given process, you can calculate the probability that the process will occur. For photon-photon scattering, the simplest Feynman diagram looks like this in concept. Two photon lines come in from the left, and two photon lines go out on the right. In between, connecting them, is a closed loop, a square or rectangle made of electron and positron lines. Each corner of this loop is a vertex, where a photon line meets an electron line. The photons do not connect to each other directly. They connect to the loop, and the loop connects to the other photons. The loop is the mathematical representation of the electron field acting as an intermediary. Now, There is a term that comes up constantly when people talk about this process, and it causes enormous confusion. That term is virtual particles. In the context of Feynman diagrams, the internal lines, the lines inside the diagram that are not the incoming or outgoing particles, are often called virtual particles. In our photon scattering diagram, the electron and positron lines forming the internal loop are called virtual electrons and virtual positrons. And this is where people frequently go wrong. When you hear the words virtual particles, you might imagine tiny, real particles that briefly pop into existence out of nothing, zip around for a fraction of a second, and then vanish again. This picture has been popularized in countless science documentaries and popular books, and it is deeply misleading. Virtual particles are not real particles that temporarily exist. They are not objects hiding in the vacuum, flickering in and out of reality like tiny ghosts. They are mathematical terms in a calculation. They are tools for bookkeeping, ways of organizing an enormously complex mathematical process into manageable pieces. Here is the more accurate way to think about it. Quantum electrodynamics calculates the probability of a process by summing up contributions from every possible way the process could occur. Some of these contributions correspond to simple, direct events. Others correspond to more complicated, indirect events involving intermediate steps. Feynman diagrams are a way of systematically listing all these contributions. Each diagram represents one way the process could, in the mathematical sense, contribute to the overall probability. The internal lines in a diagram, the virtual particles, represent these intermediate mathematical contributions. They do not represent objects that you could ever detect with a particle detector. You cannot catch a virtual electron. You cannot measure its position or momentum independently of the overall process. It does not have a definite energy and momentum the way a real particle does. It is, in a precise technical sense, off-shell, meaning it does not satisfy the normal relationship between energy, momentum, and mass that real particles obey. It exists only as part of the calculation that connects the incoming particles to the outgoing particles. This distinction matters enormously for understanding photon-photon scattering. When we say that two photons interact through a virtual electron-positron loop, we are not saying that two photons literally create a pair of electrons and positrons that then recombine to produce two new photons. That language sounds dramatic and exciting, but it gives the wrong picture. What we're really saying is that the quantum electron field allows a mathematical coupling between the two photons, and the most convenient way to calculate the strength of that coupling is by using Feynman diagrams that include an internal loop of electron lines. The loop is a calculation tool. The physical reality is simpler and yet more mysterious. The photons interact because the quantum vacuum, with its underlying charge fields, provides a mechanism for coupling that does not exist in classical physics. The charged quantum fields link the photons indirectly, and the Feynman diagram with its virtual loop is our best mathematical language for describing how strong that link is. So now we know that quantum electrodynamics allows photon-photon scattering through the intermediary of charged quantum fields. The next obvious question is, how often does this actually happen? How likely is it that two photons will scatter off each other? And the answer is, extraordinarily, almost unbelievably rarely. The probability of photon-photon scattering depends on several factors, but the most important is a number called the fine structure constant, often denoted by the Greek letter alpha. The fine structure constant is approximately 1 over 137. It is one of the most important numbers in all of physics. It quantifies the strength of the electromagnetic interaction, essentially telling you how strongly photons couple two charged particles, and it is a small number, roughly 0.0073. Now, here is where that smallness becomes devastating for photon-photon scattering. In the Feynman diagram for photon-photon scattering, there are 4 vertices, 4 points where a photon line meets an electron line. Each vertex contributes a factor of alpha to the overall probability. Since the probability involves the square of the amplitude, and each vertex contributes a factor proportional to the square root of alpha, the overall probability ends up being proportional to alpha raised to the 4th power. Alpha to the 4th is 1 over 137 multiplied by itself 4 times. That works out to roughly 1 over 350 million. And that is just the coupling constant contribution. There are additional suppression factors that make the probability even smaller, particularly at low photon energies. The cross-section, which is the physicist's way of measuring the probability of an interaction, for visible light photon-photon scattering is incredibly tiny. For photons with wavelengths in the visible range, the cross-section is on the order of 10 to the negative 65 square centimeters. To appreciate how absurdly small that number is, consider that the cross-section for an electron scattering off a photon is about 10 to the negative 25 square centimeters. The photon-photon cross-section is roughly a trillion times smaller. It is so small that if you took all the light ever produced by every star in the observable universe over the entire 14 billion year history of the cosmos, and let all those photons crisscross through space, colliding and recolliding over and over again, the expected number of visible light photon-photon scattering events would still be essentially 0. This is why you have never seen 2 flashlight beams bounce off each other. It is not that it cannot happen. Quantum electrodynamics says it can. The probability is not 0, but it is so close to 0 that it might as well be 0 for any practical purpose you could ever imagine. In everyday life, at everyday energies, with everyday photons, photon-photon scattering simply does not happen in any detectable way. The situation was first analysed in depth in the 1930s by the German physicists Hans Euler and Bernhard Kokel, working with Werner Heisenberg. They calculated the first corrections to Maxwell's equations from quantum effects and showed that the linearity of classical electromagnetism is broken at the quantum level. The quantum vacuum, with its fluctuating electron field, introduces tiny nonlinear corrections to how electromagnetic fields behave. These corrections are so small that they are utterly negligible under normal conditions, but they are there. And they mean that, in principle, strong electromagnetic fields can influence each other through the quantum vacuum. Light can scatter off light. The vacuum is not perfectly transparent. What Hans Euler, Bernhard Kokel, and Werner Heisenberg had found was something remarkable and unsettling. They had shown that Maxwell's equations, those pristine, perfectly linear equations that had governed our understanding of electromagnetism for over 70 years, were not exactly right. At the quantum level, the equations acquire tiny corrections. These corrections introduce non-linearities terms where the electromagnetic field interacts with itself, where the presence of one field affects how another field behaves. In classical electromagnetism, this simply cannot happen. The electric field from one source does not change the electric field from another source. They add together independently, and that is all. But in the Euler-Heisenberg correction, the fields do not simply add. They influence each other, subtly, weakly, almost imperceptibly, but genuinely. To understand what this means intuitively, think about what happens when sound travels through air under normal conditions. Two sounds can cross in a room and each continues on its way, just like two beams of light. The waves add together in the overlap region and then separate cleanly. But if you make the sound extremely loud, if you push the air beyond its normal range, something changes. The air itself starts to behave differently. It compresses and expands in ways that are no longer perfectly proportional to the wave's amplitude. The medium stops being perfectly linear. The waves start to distort each other. You hear harmonics, overtones, frequencies that were not in the original sounds. The waves are interacting, not directly, but through the medium they're traveling in, because the medium itself has been pushed into a regime where it no longer behaves simply. The quantum vacuum does something analogous for light, although the analogy should not be pushed too far. At ordinary energies, the quantum vacuum is an almost perfectly linear medium. Electromagnetic waves pass through it without affecting each other, just as Maxwell predicted. But at extreme energies, when the electromagnetic fields become extraordinarily intense, the vacuum's response is no longer perfectly linear. The quantum fields filling the vacuum, particularly the electron field, start to matter. They introduce a tiny but real coupling between electromagnetic waves. The vacuum starts to behave very slightly, like a non-linear medium. And in a non-linear medium, waves can interact. This is what the Euler-Heisenberg effective Lagrangian describes mathematically. It is a correction to Maxwell's equations that accounts for the quantum vacuum's response to intense electromagnetic fields. The correction is proportional to the fourth power of the field strength, which is why it is completely negligible under normal conditions. The electromagnetic fields of everyday light are fantastically weak compared to the scale at which these corrections matter. To get a sense of that scale, the critical field strength at which quantum vacuum effects become significant is called the Schwinger limit. It corresponds to an electric field of roughly 1.3 times 10 to the 18 volts per meter. For comparison, the strongest sustained electric fields produced in laboratories are about 10 billion times weaker than this. The fields from a flashlight beam are trillions of times weaker still. You would need electromagnetic fields of almost inconceivable intensity before the non-linearity of the quantum vacuum became anything more than an infinitesimal whisper. But the whisper is there, and at high enough photon energies, even without reaching the Schwinger limit in terms of raw field strength, the effective coupling between photons grows large enough to be measured. But here's the critical thing. The probability of this scattering does not stay the same at all energies. It grows. As the energy of the photons increases, the probability of interaction increases dramatically. The cross-section for photon-photon scattering scales roughly as the sixth power of the photon energy at energies well below the electron mass threshold, and even more steeply near that threshold. This means that if you double the energy of each photon, the probability of scattering increases by roughly a factor of 64. If you increase the energy by a factor of 10, The probability increases by roughly a factor of 1,000,000. At very high energies, particularly when the photon energies start approaching the rest mass energy of an electron, about 511,000 electron volts, the probability of scattering increases enormously compared to visible light photons, which carry only about 2 electron volts each. The ratio between these energies is roughly 250,000, and the probability scales as at least the 6th power of energy, becoming even steeper near that threshold. So gamma-ray photons near the electron mass threshold are incomparably more likely to scatter off each other than visible light photons. The numbers shift from essentially impossible to merely very rare. This energy dependence is absolutely central to the story. At low energies, like visible light, quantum electrodynamics predicts that photon-photon scattering exists, but is so suppressed that it has no practical consequences whatsoever. At high energies, like gamma rays, the scattering becomes strong enough that it has real, observable effects. The quantum loophole exists at all energies, but it only becomes physically significant when the photons carry enough energy to meaningfully excite the charged quantum fields in the vacuum. Low energy photons barely tickle the electron field. High energy photons can probe it much more aggressively, and the field responds much more strongly. Now, there is one more factor that dramatically affects whether two photons will interact, and it has nothing to do with the photon's individual energies. It has to do with geometry, specifically the angle at which the two photons collide. When physicists talk about particle collisions, they use a concept called center of mass energy. This is the total energy available in the collision to create new particles or to cause deflections. It is not just the sum of the two particles' energies. It depends on how the particles are moving relative to each other. Imagine two cars driving toward each other on a highway, each going 100 kilometers per hour. When they collide head-on, the relative speed of impact is 200 kilometers per hour. The collision is violent and catastrophic. Now imagine two cars driving in the same direction on the highway, one going 100 kilometers per hour and the other going 101 kilometers per hour. The faster car slowly catches up and bumps into the slower one at a relative speed of just 1 kilometer per hour. It is barely a tap. The same two cars with the same individual speeds produce vastly different collisions depending on the angle of approach. Photons work the same way. Two photons traveling directly toward each other head-on produce the maximum possible center of mass energy for their given individual energies. All of their energy is available for the interaction. But two photons traveling in nearly the same direction, almost parallel to each other, produce very little center of mass energy, even if each individual photon carries a lot of energy. Most of their energy is locked up in their collective forward motion, rather than being available for interaction. The mathematics bears this out precisely. For two photons with equal energy colliding head-on, the center of mass energy equals twice the energy of a single photon. That is the maximum. For two photons traveling in the same direction, the center of mass energy drops towards zero no matter how much energy each photon carries individually. The center of mass energy depends on the angle between them through a specific trigonometric relationship. As the angle between their paths decreases from 180 degrees, which is a head-on collision, towards 0 degrees, which is parallel travel, the center of mass energy drops rapidly. Let me give you a more concrete example of why this matters, grounded directly in the physics of photons. Imagine two gamma-ray photons, each carrying 500,000 electron volts of energy. If these two photons collide head-on, traveling in exactly opposite directions, their center of mass energy is 1 million electron volts. That is very close to the threshold for pair production, and the probability of scattering is significant by photon-photon standards. Now take those exact same two photons with exactly the same individual energies, and instead of aiming them at each other, send them in the same direction, one slightly behind the other, traveling almost parallel paths. Despite each photon still carrying 500,000 electron volts, the center of mass energy of this pair plummets. It drops to nearly zero. These two photons, each individually powerful enough to be 1/2 of a pair-producing collision, are rendered essentially harmless to each other simply because of the direction they're traveling. Their energies are still there, locked inside each photon, but the energy is all going the same way. It is like two runners sprinting side by side. They might both be fast, but they are not colliding. Their relative motion is almost zero. This example reveals something fundamental about how energy works in special relativity. Energy is not a single number that you can simply add up and spend however you like. It comes with a direction. It comes with a momentum. And the usable energy in a collision, the energy available to create new phenomena, depends not on the sum of the individual energies, but on how those energies are oriented relative to each other. Two photons with identical individual energies can produce dramatically different outcomes, depending on whether they are aimed at each other or drifting in the same direction. The angle between them is not merely a geometric detail, it is a physical variable as important as energy itself. This has enormous consequences. Whether two photons can scatter, and especially whether they can do something even more dramatic than scatter, which we will explore next, depends not just on how much energy each photon carries, but on how they approach each other. Head-on collisions are the most productive. Glancing collisions waste most of the available energy. And parallel photons, no matter how energetic they are individually, have almost no center of mass energy to work with. This is why the geometry of a photon collision matters just as much as the energy of the photons involved. Nature does not care only about how powerful each photon is. It cares about how that power is directed, about the relative angle of approach, about whether the photons are working against each other or merely drifting alongside each other. Two photons hurtling directly toward one another are in the best possible configuration for an interaction. Two photons drifting side by side are in the worst. The angle between them is not a minor detail, it is a make or break factor that determines whether the quantum loophole can produce any observable effect at all. So here is where we stand. Classical physics says photons do not interact, and this is an extraordinarily good approximation at everyday energies. But quantum electrodynamics reveals that it is only an approximation. Beneath the surface, the quantum vacuum is filled with charged fields, particularly the electron field, that allow two photons to couple indirectly. The probability of this coupling is fantastically small at low energies, suppressed by the fourth power of the fine structure constant and further diminished by factors related to photon energy. But the probability grows as photon energy increases, and the geometry of the collision matters enormously because head-on photons deliver far more center of mass energy than photons approaching at shallow angles. This is the quantum loophole. The door that classical physics kept firmly shut, quantum electrodynamics has quietly pushed open. Only a crack, only under extreme conditions, but open nonetheless. And through that crack, something extraordinary becomes possible. Because when the center of mass energy of two colliding photons exceeds a certain threshold, something far more dramatic than scattering occurs. The photons do not merely deflect each other and continue on their way. They can vanish entirely. And in their place, where there was once nothing but pure light, matter appears. Real, tangible, detectable matter. An electron and its antimatter twin, a positron, conjured into existence from the energy of two colliding photons. That process, the creation of matter from light, is what we are going to explore now. We have arrived at the part of this story that sounds the most like science fiction, and yet every single thing you are about to hear has been verified experimentally. It is not speculation. It is not theory in the colloquial sense of an educated guess. It is measured, confirmed, demonstrated fact. Two photons, two packets of pure light carrying no mass whatsoever, can collide and vanish, and in their place, where an instant before there was nothing but light, matter appears. An electron and its antimatter twin, a positron, materialize from the energy of the collision. Mass is conjured from masslessness. Substance is born from something that has no substance at all. This is not a metaphor. It literally happens. And understanding how it works requires us to grapple with one of the most profound equations in the history of human thought. In 1905, the same year he explained the photoelectric effect and laid the groundwork for quantum mechanics, Albert Einstein published his theory of special relativity. Among its many consequences was a relationship so famous that even people who know nothing about physics recognize it. E equals mc squared. Energy equals mass multiplied by the speed of light squared. This equation tells us something staggering about the nature of reality. Mass and energy are not separate things. They are two forms of the same underlying quantity. Mass is a kind of frozen energy. Energy can be converted into mass, and mass can be converted into energy. The speed of light squared is an enormous number, roughly 9 times 10 to the 16th in metric units, which means that even a tiny amount of mass corresponds to a colossal amount of energy. This is why nuclear weapons are so destructive. They convert a small fraction of their mass into energy. And because the conversion factor is so enormous, even a tiny amount of converted mass releases devastating power. But tonight we're interested in the reverse direction, not converting mass into energy, but converting energy into mass. E equals mc squared works both ways. If you have enough energy concentrated in a small enough region, the energy can transform into mass. It can create particles that were not there before. Particles with actual rest mass. Particles you can detect and measure. Particles that persist and interact with the world around them. This is what happens when two sufficiently energetic photons collide head-on. The photons themselves are massless. They have zero rest mass. They are pure energy in motion. But they do carry energy, and if that combined energy is large enough, it can be converted into the mass of new particles. The photons disappear, and in their place, an electron and a positron appear. The energy of the light has become the mass and kinetic energy of matter and antimatter. This process has a name. It is called the Bright-Wheeler process, named after the physicists Gregory Bright and John Archibald Wheeler, who first described it theoretically in 1934. Their paper laid out the mathematics showing exactly how two real photons could collide and produce an electron-positron pair. It was a prediction rooted firmly in the new quantum theory, and it has since been confirmed by experiment. The Bright-Wheeler process is the purest known example of matter being created from light. No other particles need to be present. No nucleus is required. No external electric field is necessary. Just two photons, colliding with enough energy, producing matter from nothing but light. But how much energy is enough? This is where the numbers matter, and they matter enormously. To create an electron and a positron, the two photons must supply enough combined energy to account for the rest mass of both new particles. An electron has a rest mass energy of about 511,000 electron volts. A positron, being the antimatter mirror of the electron, has exactly the same rest mass energy, 511,000 electron volts. So the minimum total energy required is twice that, roughly 1.022 million electron volts. This is the threshold. Below this combined energy, pair production simply cannot occur. It is not that it becomes unlikely or difficult. It is absolutely forbidden by the conservation of energy. You cannot create the mass of two particles if you do not have enough energy to pay for that mass. The universe enforces its energy budget strictly. There are no loans, no exceptions, and no workarounds. So the combined energy of the two photons must be at least 1.022 million electron volts. But it is not quite as simple as just adding up the energies of the two photons, because the collision geometry plays a critical role, just as it did for scattering. What matters is not the total energy in the laboratory, but the center of mass energy. The energy available in the reference frame where the combined momentum of the two photons is zero. For a head-on collision between two photons of equal energy, the geometry is ideal. The photons are traveling in exactly opposite directions, so their momenta cancel perfectly. All of their combined energy is available as center of mass energy. In this case, each photon needs to carry at least 511,000 electron volts, and together they meet the threshold of 1.022 million electron volts. That corresponds to gamma-ray photons, light with wavelengths so short and energies so high that they are produced only in the most extreme environments in the universe. But what if the photons are not colliding head-on? What if they are approaching each other at an angle? Then some of their energy is tied up in their net forward motion, their combined momentum in a particular direction. That momentum must be conserved. You cannot simply make it disappear. So some of the photon's energy goes into the kinetic energy of the resulting particles, rather than into creating their mass. The particles emerge moving through space, carrying the leftover momentum. This means that for photons colliding at an angle less than 180 degrees, the individual photon energies must be higher than the head-on minimum to compensate. The shallower the angle, the more energy each photon needs. And for photons traveling in nearly the same direction, almost parallel, the required energies become astronomical because almost all of their energy is locked in their collective forward momentum, and very little is available for mass creation. This is a point worth pausing on because it reveals something subtle and important about how energy and momentum work together. In everyday life, you might think of energy as the only thing that matters for creating something new. If you have enough energy, you can make it happen. But in relativistic physics, momentum is equally important. Energy and momentum are intertwined in ways that our everyday intuition does not prepare us for. The photons must supply not only enough energy to create the mass of the electron and positron, but they must do so while simultaneously conserving the total momentum of the system. What comes out must carry the same total momentum as what went in. This dual requirement, conserve energy and conserve momentum, constrains what is possible far more tightly than energy conservation alone. Consider a single photon traveling through empty space. This photon might carry an enormous amount of energy, far more than 1.022 million electron volts. You might think it could simply convert itself into an electron-positron pair all on its own, but it cannot. A single photon in empty space can never produce a pair, no matter how much energy it carries. The reason is momentum conservation. A photon always travels at the speed of light. An electron and a positron, having mass, always travel slower than light. There is no way to distribute the single photon's energy and momentum among two massive particles, such that both energy and momentum are simultaneously conserved. The math simply does not work out. A single photon cannot decay into a pair in empty space. This is not a minor technicality. It is a fundamental prohibition enforced by the deepest symmetries of physics. This is precisely why the Bright-Wheeler process requires two photons. When two photons collide, especially head-on, their momenta can cancel or partially cancel, freeing up energy that can go into mass. The two-photon system has the mathematical freedom that a single photon lacks. The momenta of the incoming photons can be distributed among the outgoing particles in a way that satisfies both conservation laws simultaneously. Head-on collisions are ideal because the momenta cancel perfectly, leaving zero net momentum. The electron and positron can then emerge back-to-back, flying off in opposite directions with equal and opposite momenta. Everything balances. Energy is conserved, momentum is conserved, and two new massive particles exist where none existed before. Now, what actually happens to the original photons during this process? This is a question that deserves a clear, direct answer because it often gets glossed over. The photons are gone. They do not survive the interaction. They do not pass through each other and continue on their way. They do not linger in some altered form. They are entirely consumed. Their energy and their momentum are fully transferred to the electron and the positron. The photons cease to exist, and the particles take their place. This is fundamentally different from photon-photon scattering, and the distinction is critical. In photon-photon scattering, which we explored earlier, two photons come in and two photons come out. The outgoing photons may have different directions or slightly different energies than the incoming photons, but they are still photons. Light enters and light leaves. The number and type of particles is preserved. The photons are deflected, not destroyed. In the Bright-Wheeler process, two photons come in and zero photons come out. Instead, an electron and a positron come out. Light enters and matter leaves. The particles that emerge are completely different from the particles that went in. The photons are not merely redirected or scattered. They are annihilated. Their energy reborn as mass. This is not scattering. This is transformation. It is a qualitative change in the nature of what exists, from massless radiation to massive matter. You can think of it as sitting on a spectrum of possible outcomes when two photons meet. At one end of the spectrum, the most common outcome by an overwhelming margin is nothing at all. The photons pass through each other without any interaction. At the next level, extraordinarily rare but possible, is scattering. The photons deflect each other slightly, changing direction but remaining as photons. And at the far end of the spectrum, the most dramatic outcome, requiring the most energy, is pair production. The photons are destroyed and matter is created in their place. Each outcome requires more energy and more precise conditions than the last, and each is rarer than the last. Let me put the energy threshold into perspective, because the numbers are astonishing. A typical photon of visible light, the kind your eyes can detect, carries an energy of about 2 electron volts. Red light is around 1.8 electron volts. Blue light is around 3 electron volts. These are the photons streaming from your screen right now, bouncing off the walls around you, entering your eyes and forming images on your retina. To produce an electron-positron pair through the Bright-Wheeler process, the combined center of mass energy must reach at least 1.022 million electron volts. That is 1,022,000 electron volts. Compare that to the 2 electron volts carried by a visible light photon. The threshold is roughly 500,000 times higher than the energy of a single visible photon. Even if 2 visible photons collide head-on, their combined energy is about 4 electron volts. The threshold is over 250,000 times greater than that. Think about what this ratio means in practical terms. Imagine you need to lift a boulder that weighs 250,000 kilograms, and all you have is a feather that weighs 1 gram. You would need 250 million feathers just to match the weight of the boulder. That is the kind of mismatch we are talking about. Visible light photons are so far below the pair production threshold that the idea of 2 of them creating an electron and a positron is beyond hopeless. It is like expecting 2 candle flames to melt a planet. The energy gap is not just large, it is vast beyond description. So when 2 visible light photons cross paths in your living room, pair production is not merely unlikely. It is impossible. There is simply not enough energy, not even close. The only photons energetic enough to approach the Bright-Wheeler threshold are gamma rays, the most energetic form of electromagnetic radiation. Gamma rays are produced in extreme environments: nuclear reactions, particle collisions, the violent neighborhoods around black holes, the explosions of dying stars. These are not the photons you encounter in everyday life. You will never produce a gamma ray with a flashlight. You will never encounter one from a laser pointer or a television screen. Gamma rays are the photons of extreme physics, born in environments of extraordinary violence and energy. This is an important point to be completely clear about. 2 ordinary beams of visible light cannot produce matter. Period. It does not matter how bright the beams are. It does not matter how many photons are in each beam. Brightness increases the number of photon pairs that could potentially interact. But if each pair falls below the energy threshold, no amount of intensity can compensate. You cannot substitute quantity for quality in this case. 1 trillion low-energy photons are no substitute for 2 high-energy ones. The threshold is a hard boundary enforced by the conservation of energy, and no amount of cleverness or engineering can circumvent it with ordinary light. The universe does not offer workarounds on this point. Now, there is something worth understanding about why the electron and the positron are the particles that get produced, rather than some other pair. The answer has to do with mass hierarchy. The electron is the lightest charged particle known to physics. Its rest mass energy of 511,000 electron volts represents the lowest possible threshold for creating a charged particle-antiparticle pair from photons. If the photons carry more energy beyond the minimum threshold, other possibilities open up. With enough energy, you could in principle produce a muon-antimuon pair. Muons are heavier cousins of the electron, carrying the same electric charge but with a rest mass about 207 times greater. The threshold for muon pair production is correspondingly about 207 times higher than for electron-positron production. At even higher energies, you could produce heavier pairs still. But the electron-positron pair is always the easiest to produce because it requires the least energy. Nature takes the path of least resistance. The electron's antimatter partner, the positron, deserves a moment of attention here. The existence of antimatter was predicted theoretically by the British physicist Paul Dirac in 1928, several years before the Bright-Wheeler paper. Dirac was working on a relativistic equation for the electron, trying to combine quantum mechanics with special relativity. His equation had two sets of solutions. One described electrons with positive energy, as expected. The other described something strange, particles with the same mass as the electron, but with the opposite electric charge. Dirac initially struggled to interpret these solutions, but eventually proposed that they described a new kind of particle, the anti-electron, later named the positron. In 1932, the American physicist Carl Anderson detected the positron experimentally in cosmic ray observations, confirming Dirac's prediction. Anderson saw a particle track in a cloud chamber that curved in the opposite direction from an electron in a magnetic field, indicating it had positive charge, but it had the same mass as an electron. It was the first antiparticle ever observed, and its discovery confirmed one of the most remarkable theoretical predictions in the history of physics. When an electron and a positron meet, they annihilate each other. Their mass is converted back into energy, typically in the form of two photons flying off in opposite directions, each carrying 511,000 electron volts. This annihilation process is the reverse of the Bright-Wheeler process. In pair production, two photons become an electron and a positron. In annihilation, an electron and a positron become two photons. Matter becomes light, and light becomes matter. The two processes are mirror images of each other, connected by the fundamental equivalence of mass and energy. This reversibility is not a coincidence. It is built into the mathematical structure of quantum electrodynamics. The theory treats particles and antiparticles symmetrically, and it treats creation and annihilation as complementary processes. If one is possible, the other must be as well, related by precise mathematical rules. The existence of the Bright-Wheeler process is, in a sense, demanded by the existence of electron-positron annihilation. If matter can turn into light, then light must be able to turn into matter. The equations insist on it. Let me be precise about one more thing, because it matters for the physics, and because it addresses a common misconception. When I say that photons can create matter, I do not mean that matter is created from nothing. Energy is not nothing. Photons carry real energy and real momentum. The mass of the electron and positron comes from that energy. E equals mc squared tells us that mass and energy are equivalent. And the Bright-Wheeler process is simply a conversion from one form to the other. No energy is created. No energy is destroyed. The total amount of energy before the collision carried by the two photons is exactly equal to the total amount of energy after the collision, carried by the electron and positron in the form of their rest mass energy plus their kinetic energy. Conservation of energy holds perfectly. Nothing is conjured from a void. The energy was there all along in the photons. It simply changed form. This distinction matters because it separates physics from magic. In magic, things appear from nothing. In physics, things transform. The energy was always present. It just changed its costume, converting from the energy of massless radiation into the mass energy and kinetic energy of massive particles. The total energy budget of the universe is unchanged. The ledger always balances. There is one more subtlety about pair production that is worth understanding, and it connects back to the distinction between the Bright-Wheeler process and other forms of pair production that are more commonly observed in laboratories. The Bright-Wheeler process, the direct conversion of two real photons into an electron-positron pair, is extremely rare. So rare that it was one of the last fundamental predictions of quantum electrodynamics to be directly confirmed by experiment. The reason is practical. It is very difficult to create two intense, focused beams of gamma-ray photons and aim them at each other precisely enough for the process to occur at a detectable rate. Gamma rays are hard to produce, hard to focus, and hard to aim. Unlike visible light, which can be guided with mirrors and lenses, gamma rays pass through most materials. Building a gamma-ray laser is far beyond current technology. So while the Bright-Wheeler process is theoretically clean and beautiful, it is experimentally very challenging. In practice, pair production is observed much more commonly in a related but different process. When a single high-energy photon passes close to the electric field of an atomic nucleus, it can convert into an electron-positron pair. The nucleus provides a kind of backdrop, a source of momentum that absorbs the recoil and allows the conservation laws to be satisfied. This is not the Bright-Wheeler process because the photon is interacting with the electric field of a nucleus rather than with another photon, but the underlying physics is related. The photon's energy is being converted into mass, and the conservation of energy and momentum are being maintained, just with the help of a nearby charged object rather than a second photon. This nuclear-assisted pair production is how positrons were first observed by Carl Anderson. Cosmic rays, high-energy particles from space, strike atoms in the upper atmosphere and produce showers of secondary particles, including gamma rays. Those gamma rays then interact with the electric fields of atmospheric nuclei and produce electron-positron pairs. Anderson detected the positrons from these pairs in his cloud chamber. He was observing pair production, but not the Bright-Wheeler variety. The nucleus was providing the extra momentum needed to make the process work with a single photon. The Bright-Wheeler process, the clean two-photon to pair conversion with no nucleus or other particle involved, is purer but rarer. It has been observed indirectly and in closely related forms, but the definitive, clean demonstration of two real photons producing a pair with no other particles present has been extraordinarily difficult to achieve. We will talk about the experimental evidence in more detail shortly. Before we move on, let me paint one final picture to help you feel the strangeness and the beauty of what we have been discussing. Imagine two gamma-ray photons hurtling toward each other from opposite directions through the emptiness of space. They are traveling at the speed of light, as all photons must. They carry no mass. They have no substance in the traditional sense. They are oscillations of electric and magnetic fields, ripples in the fabric of electromagnetism, as insubstantial as anything in the physical universe, and then they meet. For an instant, their energies overlap in a single point, and in that instant, something remarkable happens. The photons vanish, the light is gone, and in its place, two brand new particles burst into existence. An electron and a positron, tiny but real, carrying mass and electric charge, spinning and flying apart from the point where the photons met. Where there was light, there is now matter. Where there was energy without mass, there is now mass with energy. The universe has performed an act of transformation so fundamental that it sits at the very heart of how reality works. These new particles are real in every sense of the word. The electron carries the same negative charge, the same mass, the same quantum properties as every other electron in the universe. The positron carries the same positive charge, the same mass, the same properties as every other positron. They are indistinguishable from electrons and positrons created by any other process. You could not examine them and determine that they were born from light rather than from some other process. They are full, legitimate members of the material world, created from nothing but the energy of two colliding photons. This is what E equals mc squared actually means in practice. Not just a formula on a blackboard, not just an equation in a textbook, but a real physical process in which the boundary between light and matter dissolves, in which the distinction between energy and mass reveals itself to be nothing more than a difference of form, not a difference of substance. Light can become matter. Matter can become light. The universe does not distinguish between them at the deepest level. They are the same thing, expressed in different ways. And all of this, the scattering, the pair production, the transformation of light into matter, begins with two photons meeting in the right way at the right energy. Two packets of light that, in everyday life, would pass through each other without the faintest whisper of interaction. The same photons that fill your room right now, bouncing off walls and streaming through windows, oblivious to each other's existence. Those photons, given enough energy and the right collision geometry, could create matter. They almost never do, because everyday photons carry absurdly little energy compared to the threshold. But the mechanism is there. The physics allows it. And in the most extreme environments the universe has to offer, it happens. What remains now is to look at the evidence, to see how physicists have confirmed these extraordinary predictions, not just in theory but in actual experiments, and to discover that the universe itself, across its vast stretches of intergalactic space, provides the most dramatic demonstration of all, one that affects the very light we receive from the most distant and violent objects in the cosmos. Everything we have explored so far, the quantum loophole in the transparency of light, the scattering of photons through charged quantum fields, the creation of matter from pure light through the bright Wheeler process, all of it was born as theory. Equations on paper. Predictions scratched into notebooks by some of the most brilliant minds of the 20th century. But physics is not mathematics. Physics demands evidence. A prediction, no matter how elegant or internally consistent, means nothing until nature confirms it. And the predictions of quantum electrodynamics regarding photon-photon interactions were extraordinarily difficult to test. Not because anyone doubted the theory. Quantum electrodynamics had proven itself spectacularly accurate in hundreds of other predictions, but because the effects were so fantastically rare, so deeply suppressed at accessible energies, that detecting them required pushing experimental technology to its absolute limits. The central challenge is straightforward to state and nightmarish to solve. You need photons of extreme energy colliding at favorable angles in sufficient numbers, with detectors precise enough to identify the vanishingly rare events where two photons actually interact amid the overwhelming flood of events where nothing happens at all. This is like trying to hear a single whispered syllable in the middle of a stadium full of screaming fans. The signal is real, but the noise is deafening. Isolating the signal requires extraordinary ingenuity. Physicists found a way, not by building gamma-ray lasers, which remained far beyond our technology, but by exploiting a phenomenon that nature provides for free in particle accelerators. When heavy atomic nuclei are accelerated to nearly the speed of light, their electric fields become enormously concentrated and intensified by relativistic effects. A lead nucleus, the nucleus of a lead atom, contains 82 protons. Each proton carries a positive electric charge. When this nucleus is accelerated to nearly light speed, its electric field gets compressed and amplified into what is effectively a dense cloud of photons traveling alongside it. These are not photons in the ordinary sense of light beams you can see. They are virtual photons, manifestations of the intense electromagnetic field surrounding the speeding nucleus. But for the purposes of photon-photon interactions, they behave enough like real photons that the physics applies. At CERN, the European Organization for Nuclear Research, the Large Hadron Collider accelerates lead nuclei to energies of several trillion electron volts per nucleus. When two lead nuclei pass very close to each other but do not actually collide, what physicists call an ultra-peripheral collision, their intense electromagnetic fields overlap. The photons from one nucleus can interact with the photons from the other nucleus. And in extraordinarily rare cases, two of those photons scatter off each other, deflecting slightly and flying off at angles that the detector can measure. The ATLAS experiment, one of the massive detectors straddling the Large Hadron Collider's beamline, was designed to detect a vast range of particle interactions. In 2017, the ATLAS collaboration reported the first direct evidence of light by light scattering at high energy. They observed events in which two lead nuclei pass close to each other, and two photons emerge from the interaction region at angles consistent with photon-photon scattering, with no other particles produced. The lead nuclei themselves continued on their way, slightly deflected but otherwise intact, having served merely as the sources of the photons that interacted. By 2019, the collaboration had accumulated enough data to confirm the observation with high statistical significance. Light had been observed scattering off light. The quantum loophole, predicted decades earlier, was real. Let me be precise about what ATLAS detected. They did not observe two flashlight beams bouncing off each other. They observed individual scattering events, one at a time, in a detector the size of a building, sifting through billions of collisions to find a tiny handful of events. Just 13 in the initial dataset, where the signatures matched the prediction of photon-photon scattering. Each event was a tiny, faint whisper in an ocean of noise. Finding them required years of data collection and painstaking analysis, but they were there, exactly where quantum electrodynamics said they would be, with exactly the properties the theory predicted. Those 13 events deserve a closer look, because they reveal just how painstaking this kind of physics really is. Out of billions upon billions of collision events recorded by the detector in the 2017 analysis, just 13 match the signature of light, scattering off light. The expected number of background events, interactions that could mimic the signature of photon-photon scattering, but actually came from other processes, was estimated at fewer than 3. So 13 events against a background of fewer than 3 was statistically significant, enough to claim evidence, but not yet enough to claim definitive discovery in the strict language of particle physics. By 2019, after accumulating more data from additional runs with LED nuclei, the number of candidate events grew substantially, and the statistical significance crossed the threshold that physicists require for a formal discovery. The result was no longer tentative, it was confirmed. But consider what this required. The Large Hadron Collider, the most powerful and expensive scientific instrument ever built, a 27-kilometer ring of superconducting magnets buried beneath the Swiss-French border, cooled to temperatures colder than outer space, accelerating lead nuclei to 99.999% of the speed of light, smashing them together millions of times, recording the aftermath with a detector weighing 7,000 tons, filled with millions of individual sensor elements, each one precisely calibrated, all of it feeding data into computing networks spanning the globe. All of that staggering infrastructure, all of that collective human effort spanning decades of design and construction and operation to find 13 events, 13 whispers of light, deflecting light in a hurricane of particle debris. That is how rare photon-photon scattering is. Even under the most extreme conditions humans can create, even with the most powerful accelerators and the most intense electromagnetic fields we can generate, it barely happens. And yet, it does happen. 13 events became dozens, and dozens became a confirmed discovery. The quantum loophole that theory had predicted was there, exactly as described, hiding in the data waiting to be found by physicists patient enough and ingenious enough to look. There is something worth appreciating about the way Atlas identified these events. The key signature is distinctive. In an ultra-peripheral lead-lead collision where light-by-light scattering occurs, you see 2 photons flying out of the interaction region and nothing else. No other particles, no debris. The LED nuclei survive intact because they never actually touched each other. Their electromagnetic fields interacted at a distance, and the only products of that interaction are 2 scattered photons. This clean, quiet signature, 2 photons and nothing else, stands out against the noisy, debris-filled signatures of actual nuclear collisions. It is precisely this cleanness that allowed the Atlas team to identify the events. In a detector designed to observe the most violent particle collisions imaginable, the signal for light-by-light scattering was paradoxically one of the quietest, gentlest events the detector could record. 2 photons emerging from the meeting of 2 speeding lead nuclei like a whisper between 2 passing freight trains. A closely related and equally remarkable result came from the STAR experiment at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory. This accelerator collides gold nuclei rather than lead nuclei, but the principle is the same. Gold nuclei carry 79 protons each, generating intense electromagnetic fields when accelerated to near-light speeds. In 2021, the STAR collaboration reported something extraordinary. They had detected electron-positron pairs emerging from ultra-peripheral gold nucleus collisions in a pattern consistent with the bright Wheeler process. 2 photons from the electromagnetic fields of passing gold nuclei had collided and produced matter. An electron and a positron, created from light. This was not quite the idealized, clean, textbook, bright Wheeler process involving two isolated photons meeting in otherwise empty space. The photons originated from the fields of heavy nuclei rather than from independent light sources. But the underlying physics, two photons interacting through the quantum vacuum and producing an electron-positron pair, was the same. The star result was the closest any experiment had come to directly observing the process that Gregory Bright and John Archibald Wheeler had predicted in 1934. Nearly 9 decades of theoretical prediction finally confirmed. There was also an earlier experiment that deserves mention, though it involved a somewhat different process. In 1997, at the Stanford Linear Accelerator Center, an experiment designated E-144 achieved something remarkable with a different approach. Instead of using two beams of photons, the experiment used a high-energy electron beam and an extremely intense laser. The electrons, accelerated to an energy of about 46 billion electron volts, collided with a powerful laser pulse. In the collision, an electron would absorb several laser photons simultaneously and emit a single, very high-energy gamma ray. That gamma ray would then collide with additional photons from the same laser pulse, and the combined energy of the gamma ray and the laser photons was enough to produce an electron-positron pair. This was not a clean two-photon process, it was a multi-photon process, requiring the simultaneous interaction of several photons. But it demonstrated something essential. It showed that photon-photon collisions could create matter in a real laboratory, not just in equations. The experiment detected positrons emerging from the interaction region, particles that had no business being there unless light had created them. It was a landmark achievement, one of the first direct demonstrations that energy in the form of light could be converted into the mass of material particles. Taken together, these experiments confirm the predictions of quantum electrodynamics about photon-photon interactions. Light-by-light scattering is real. Pair production from photon collisions is real. The quantum vacuum, with its charged fields, genuinely permits photons to interact. The effects are rare, demanding extreme energies and sophisticated detectors, but they are unmistakably there. But the most dramatic demonstration of photon-photon interactions does not come from any laboratory on Earth. It comes from the universe itself, and it operates on a scale so vast that it affects the very light we receive from some of the most distant and violent objects in the cosmos. Deep in intergalactic space, far from any star or galaxy, space is not truly dark. It is filled with a faint, diffuse glow of photons called the extragalactic background light. This is the accumulated light of every star that has ever shone and every galaxy that has ever existed, stretching back billions of years. Starlight emitted by the first galaxies, light from stars that died long ago, infrared radiation re-emitted by dust that absorbed starlight, all of it fills the universe with a faint bath of photons. You cannot see it with your eyes because it is far too dim, but it is there, measurable with sensitive instruments, and it is everywhere. There is no region of intergalactic space that is free of this background glow. Now imagine a gamma ray photon, an extremely high energy photon produced in one of the most violent environments the universe has to offer. Perhaps it was born in a blazar, a type of active galactic nucleus, where a supermassive black hole at the center of a distant galaxy is consuming matter and launching jets of particles and radiation at nearly the speed of light, aimed almost directly at Earth. These jets produce gamma rays with energies in the billions and trillions of electron volts, far above the threshold for the bright Wheeler process. This gamma ray photon leaves the blazar and begins its long journey across intergalactic space toward Earth. Along the way, it must pass through the extragalactic background light, that faint sea of infrared and visible photons filling all of space. And here is where the bright Wheeler process becomes a cosmic phenomenon. The gamma ray carries enormous energy. The background photons carry relatively little energy individually, perhaps a fraction of an electron volt for an infrared photon. But when a trillion electron volt gamma ray collides head-on with an infrared background photon, the center of mass energy can exceed the pair production threshold. The gamma ray and the background photon annihilate each other and produce an electron-positron pair. The gamma ray is destroyed. It never reaches Earth. This process is not hypothetical. It happens constantly across the universe. High-energy gamma rays from distant sources are steadily absorbed by collisions with background light. The farther the gamma ray has to travel, the more background photons it encounters, and the higher the probability that it will be absorbed before reaching us. This creates what physicists call the gamma ray horizon, a distance-dependent limit on the highest energy gamma rays that can reach Earth from any given direction. For gamma rays with energies around 1 trillion electron volts, the universe becomes significantly opaque over distances of a few billion light years. A blazar 2 billion light years away will have its highest energy gamma rays substantially dimmed by the time they reach our telescopes. A blazar 10 billion light years away will have its highest energy gamma rays almost entirely absorbed. The universe acts as a filter, selectively removing the most energetic photons from the light of distant objects through photon-photon pair production. This effect has been observed directly. The Fermi Gamma Ray Space Telescope, orbiting Earth since 2008, has surveyed the gamma ray sky with unprecedented sensitivity. Ground-based gamma ray observatories, large arrays of telescopes that detect the faint flashes of light produced when gamma rays strike Earth's atmosphere, have observed gamma ray sources at energies reaching into the trillions of electron volts. When astronomers compare the gamma ray spectra of nearby blazars to those of distant blazars, the difference is unmistakable. Distant blazars show a clear suppression of their highest energy gamma rays, exactly the pattern predicted by the bright Wheeler process operating on a cosmic scale. The more distant the blazar, the stronger the suppression. One famous example is the blazar Marker Re and 501, located about 450 million light years from Earth. Observations of this blazar at very high energies show spectral features consistent with partial absorption by the extragalactic background light. By comparing the observed spectrum to theoretical models of what the spectrum should look like without absorption, astronomers can actually measure the density of the extragalactic background light itself. Photon-photon pair production has become not just a confirmed prediction of quantum electrodynamics, but a practical tool for studying the faint background glow that fills the universe. Think about what this means. The bright Wheeler process, the transformation of light into matter, is happening throughout the cosmos at every moment. High-energy gamma rays from distant blazars and other extreme sources are being absorbed by collisions with background starlight, their energy converted into the mass of electron-positron pairs that then scatter and lose energy in intergalactic space. The universe is continuously converting light into matter through the very mechanism we have been exploring tonight. Not in laboratories, not in controlled experiments, but across billions of light years of intergalactic space on a scale that dwarfs anything humans could ever build. And yet, in your living room, none of this matters. The photons from your lamp and the photons from your screen pass through each other with serene, total indifference. Nothing happens. Nothing can happen. And that brings us to a point worth stating clearly one final time. Because the contrast between what is possible in principle and what actually occurs in everyday life is at the heart of this entire story. Two ordinary visible light photons do not produce detectable matter. They never have, and barring some revolution in physics that overturns everything we know, they never will. The energy gap between a visible photon and the pair production threshold is so immense that the process is not merely unlikely at everyday energies, it is forbidden. Scattering between visible photons is technically allowed by quantum electrodynamics, but the probability is so crushingly small, so profoundly suppressed, that it has no practical consequence anywhere in the observable universe under normal conditions. The classical picture of light passing through light without interaction is, for every purpose you will ever encounter in your life, perfectly, unimprovably correct. The quantum effects we have been discussing tonight live at the very edge of what is physically possible. They require either extraordinary energies, like the gamma rays from blazars, and the relativistic fields of heavy nuclei at the Large Hadron Collider, or they require the accumulated effects of photons traveling across billions of light years of space, encountering trillions upon trillions of background photons along the way. In no everyday scenario, in no earthly laboratory using ordinary light, do these effects play any detectable role. The loophole exists, but for visible light, the loophole is so narrow that nothing fits through it. So now let us answer the question we start with. What happens when two photons collide? The answer is not one thing. It is a spectrum of possibilities, and which possibility occurs depends almost entirely on two factors: the energy of the photons and the geometry of their encounter. At everyday energies, with visible light photons, the answer is simple and definitive: nothing. The photons pass through each other as though the other does not exist. The probability of any interaction is so vanishingly small that it has never been observed and almost certainly never will be with ordinary light. Maxwell's classical prediction that light does not interact with light holds with extraordinary precision. If you cross two flashlight beams in a dark room, they will overlap. Their fields will temporarily add together in the crossing region, and then each beam will continue on its original path, completely unchanged. This is what happens every time photons from different sources cross paths in your daily life, and it is what makes vision, photography, astronomy, and optical communication possible. At higher energies, things change. Quantum electrodynamics predicts that photon-photon scattering becomes possible through the interaction of charged quantum fields in the vacuum. The probability, while still extremely small at moderate energies, grows as the photon energy increases. At energies approaching the rest mass of the electron, the scattering cross-section becomes large enough to detect with sufficiently powerful accelerators and sensitive detectors. This has been observed at the Large Hadron Collider using photons from the electromagnetic fields of relativistic LED nuclei. In these events, 2 photons enter the interaction region and 2 photons leave, deflected to new angles. Light has scattered off light. The photons are not destroyed, they are redirected. At the highest energies, when the center of mass energy of 2 colliding photons exceeds about 1.022 million electron volts, a new possibility emerges. The photons can annihilate each other entirely, and in their place, an electron and a positron appear. This is the bright Wheeler process, the direct creation of matter from light. The original photons cease to exist. Their energy and momentum are fully converted into the mass and motion of the newly created particles. This process has been observed in collider experiments and operates on a cosmic scale across intergalactic space, where high-energy gamma rays are absorbed by collisions with background starlight. The collision angle matters as much as the energy. Head-on collisions deliver the maximum center of mass energy, giving the photons the best chance of interacting. Photons approaching at shallow angles waste most of their energy in collective forward motion. Parallel photons, no matter how energetic, have essentially zero center of mass energy and cannot interact at all. Geometry is not a minor detail, it is a determining factor. So the full answer stretches across a vast range. At one end, perfect transparency. 2 photons meet and nothing happens. At the other end, utter transformation. 2 photons meet and matter is born from light. Between these extremes lies the rare but real possibility of scattering, where photons deflect each other without being destroyed. Where you land on the spectrum depends on what kind of photons you're talking about, how much energy they carry, and how they approach each other. For the photons in your living room, the answer is always nothing. For the photons in the heart of a particle collider, the answer can be scattering or pair production. For the gamma rays streaking across billions of light years of intergalactic space, the answer is the gradual, steady absorption of the most energetic light the universe produces, converted one pair at a time into the mass of electrons and positrons that scatter and fade into the cosmic background. There is something deeply beautiful about this picture. We began with the simplest possible observation: 2 beams of light crossing in a room without affecting each other. And from that simple observation, we followed a thread that led us through classical electromagnetism, through the quantum revolution, through the strange and counterintuitive world of quantum fields and virtual processors, through the most powerful particle accelerators ever built, and out into the vast reaches of intergalactic space. At every step, the same physics governed what happened. The same quantum electrodynamics that predicts the transparency of your living room also predicts the opacity of the distant universe to the highest energy gamma rays. The same theory that explains why your flashlight beams pass through each other also explains how matter can be conjured from pure light in the fields of colliding nuclei. One theory, one set of equations, spanning the entire range from perfect transparency to utter transformation. And perhaps the most remarkable thing of all is this: you are made of matter. Electrons, protons, neutrons, the atoms that build your bones and your brain, and the eyes you're using to take in these words. And the laws of physics say that matter like this can be created from light. Not easily, not often, but under the right conditions, the energy of 2 colliding photons can become the mass of particles no different from the ones you are made of. There's no fundamental barrier between light and matter. They are expressions of the same underlying reality, connected by the deepest equations physics has ever produced. The light filling the room around you and the matter making up your body are not as different as they appear. They are related. They can transform into each other. The boundary between them is not a wall. It is a threshold, and with enough energy, it can be crossed. Tonight, the next time you look at a beam of light, whether it is the glow of a lamp, the flash of headlights on a dark road, or the faint shimmer of starlight reaching you from hundreds of light years away, remember what you now know. Those photons are almost always invisible to each other. They pass through one another without the faintest acknowledgement, carrying their energy and information across the room or across the cosmos in perfect isolation. But beneath that serene transparency, hidden in the quantum fabric of the vacuum itself, there is a mechanism that allows the impossible. Two photons can meet and deflect. Two photons can meet and create matter. The light around you is not as passive, not as harmless, not as simple as it seems. It is capable of something extraordinary, and the only things standing between ordinary light and the creation of matter are energy and geometry. That is what happens when two photons collide. Almost always, nothing. Rarely, a whisper of deflection. And in the most extreme circumstances the universe has to offer, something miraculous, light becomes matter. And the universe reminds us once again that reality is far stranger and far more wonderful than it appears.